My name's Alex Chapman, this is Paul Stone, and this is our talk, Toxic Proxies, Bypassing HTTPS and VPNs to Pwn Your Online Identity. So first off, thank you all for coming here on a Sunday afternoon. Really good to see so many people turning out for this, so thank you very much, and we'll get started. So, okay, first we're going to start with the demo. Demo video, assuming this works. So, this is what this is an example of this thing we're going to be talking to you about today. And this is actually about being able to extract information from HTTPS streams on a local network. You'll see some of the information there. So instead of just the boring who we are slide, that's kind of just a very quick demo of the sort of thing we're going to be showing you. So as I said, my name's Alex Chapman, my colleague Paul Stone. We both work for Context Information Security in the UK. I'm Noxinet on Twitter, and PDJ Stone standing next to me. I'll explain that demo in a little bit more detail as we go through. So, this is our talk, the exciting introduction, which you all just saw. I hope everyone else found it as exciting as I did. We're going to have to start with some history. This is the 101 track. We're going to talk a little bit about the problem space, what's been going on there, how we got to where we are today, and how the attack we're going to describe kind of fits into all of that. So then we're going to explain the attack. We're going to show how you can sniff data from HTTPS streams. We're going to steal that data. We're going to actually do something with it, and we're going to show how it can ultimately be used to kind of steal your online accounts. We're then going to talk a little bit about VPNs and how they protect us or not against this, and then put in place some real mitigations about what we should be doing on these systems to help make them more secure. And then we'll talk a little bit about the fixes that have been put in place by various vendors around these issues. So, where we're starting. This is a kind of attack that we're looking at from a rogue access point perspective. So rogue access points tend to have reasonably privileged access to a network anyway. You control the DNS, DHCP, all the rest of it. So you're already in a position where you can kind of monitor and intercept data. Good, still good. So back in the day, 1993. No encryption, right? So we're here, we're on a Mosaic browser, browsing away. Everyone can see everything that's going on. And then somebody kind of thought, well, what if I want to do something sensitive over this? So we added opt-in encryption. So we're talking SSL here. So Netscape 2 shipped with SSL in 1995. So again, a good 20 years ago. Users are somewhat safe from passive sniffing attacks. We obviously know nowadays that the SSL back then was awful and terribly, terribly broken, but at the time, it was what we needed it to be. But SSL wasn't perfect, so a lot of websites allow connecting over both HTTPS and HTTP and HTTPS. People connect to HTTP first, because who writes in the S when they're putting in their URLs, who even puts in the schema. And evil man-in-the-middle attacks can prevent users from reaching the HTTPS sites and having to fall back to the unencrypted sites. So it wasn't great. And Moxie Mullen Spike demonstrated this in 2009 with SSL Strip. Great tool for the sign, for man-in-the-middling these connections, downgrading them all to HTTP, and the only indication to the user was the kind of padlock in the corner of the screen wasn't there. And again, a lot of users wouldn't be checking that anyway. Just a quick example of SSL Strip for those who haven't seen it before. Browse to a HTTP site. What it's supposed to do is redirect to the HTTPS with a 302 redirect. SSL Strip in the middle of that will actually prevent that redirection from happening. So SSL Strip broke HTTPS connections by simply ignoring them and stripping them out of the string. And browser vendors obviously had to do something about this to make their connections and connections to websites much more secure. So this is where we introduced HTTP strict transport security. And this is somewhere around 2010. So again, a good 6 years ago. That's now been picked up by a lot of major websites. A big news article the other day about Google.com going HSTS. So it's taking a while, but it is going there. And HSTS essentially prevents browsers from requesting the plaintext HTTP resource in the first place. So we don't have the option of doing the SSL strip. That's kind of where we are in the present day. HSTS is doing a pretty good job. So nearly all traffic to the sites we use on a daily basis is encrypted with HTTPS, HSTS protected. So theoretically, now we're in the coffee shop, in the pub, on our laptops, we should be fine. Right? We need a new style of attack, and this is something we came across about 6 months ago now, and show the attack to you, show how it can be used, and what we've been able to do with it. So I'll hand over to Paul to start the explanation.
Okay, hello. So Alex has given you a bit of history, and I'm going to give you a little bit more history, so just bear with us till we get onto the fun new stuff. So just to introduce pack files for people who haven't heard about them before. Pack files exist because large companies have very complex internal networks, lots of different proxies, and they need some way to be able to figure out which proxy to connect to depending on the site that you want to visit. So a pack file is simply a small bit of JavaScript that the browser asks the JavaScript, says, I want to visit this URL, and the JavaScript figures out which proxy to visit, which proxy to use, and it returns a proxy as a string. This was invented in 1996 by Netscape, so it's their fault. So the other piece of the puzzle that kind of complements pack is WPAD. So WPAD is essentially if your browser doesn't have a pack file, then WPAD tells it which pack file to use and where to go and get the pack file. So WPAD was invented in 1999, and Microsoft's name is on this ETF draft, so it's kind of their fault. So there's a few ways to do WPAD. You can do it via DHCP. You can kind of the gateway, you can push it to the OS or to the browser after it fetches an IP. And there's various other things as well. So DNS lookups with this, it will use the DNS suffix and look up like wpads.internal.company or whatever. And there's also NetBIOS, LLMNR, and all that as well. So there's lots of ways that WPAD can work. So the WPAD attacks are very well known. There are a whole bunch of tools that will make it very simple to inject or spoof WPAD responses. And if you can do that, you can then target one machine or a whole bunch of machines and hijack all their traffic and route their traffic, their web traffic, through your malicious proxy. So that means that all plain text, non-HTTPS traffic can be modified and viewed by the attacker. So there's a bit we quite enjoyed from reading the WPAD spec. It says, minimally, it can be said that the WPAD protocol does not create any new security weaknesses. It's kind of famous last words there. Did you want to?
Yeah. Yes. So yeah, just really quick overview of how these things get pushed out. So a laptop on a network asks the router for HTTP options. The router can then respond with option 252. Which is the URL to a pack file that the system will then go download and use as its pack file for choosing proxies to get out to the internet. Alternatively, if it doesn't receive a pack file through that, it'll do a DNS lookup for wpad.search domain, so the search domain that was either pre-configured or was pushed out over DHCP. If the router's responds to that, it can then respond with the IP of a host, which can serve a pack file, and in this case, we'll obviously be serving malicious pack files. The last method is from on a network with a malicious actor that's on the same network as you, so not actually on the router. So if the system still hasn't got a pack file, it'll send out a link local multicast name resolution request for WPAD. So if you've ever opened up Wireshark on a Windows network, you'll see loads of requests for things like WPAD, just being broadcast to other systems on the network. If any other system on that network responds, that system, the user system will use that response to go and grab the pack file from the IP address given there. I think I hold back to you. So Windows has had WPAD turned on by default, and this is even in Home Edition. So this is a very kind of corporate thing. There's no reason to have this on your home network. But it's still, in Windows 10, enabled by default. Local network attackers can exploit this, and there are tools there. Paul showed a link to it earlier. But fortunately, again, with these HTTPS and HSTS traffic, there's theoretically, at this point, nothing the attacker should be able to do to our connections to kind of get at our data. And that's what we're going to show you next. So throughout this research, we kind of wanted to follow the trend of naming our vulnerabilities. And we've got a few kind of rejected titles. And this was one of my favorite, Breaking WPAD. Paul actually did the posters for this, and I think he probably spent more time on that than this actual talk. But hand back.
Okay, a little bit more theory before we get to the really fun stuff. So what does a pack script look like? So a typical pack script might look a bit like this. So the idea is that there's 3 different proxies, and depending on what the hostname ends in, it will route the browser to one of the 3 proxies. So every pack script has to define this function with this exact name called find proxy for URL, and it takes 2 parameters, the full URL and the hostname. So most pack scripts will just look at the host and make a decision based on the suffix and say, use this proxy or this proxy. Very simple. So, like I said, it's this one function called find proxy for URL. And according to the spec, it takes the full URL and the hostname as parameters and returns a string. In this case, it returns direct, which means don't use any proxy. So it's the full URL that gets passed into this pack script, which is potentially a malicious pack script. Can anyone see the problem yet? So the full HTTPS URL is now known by this attacker's piece of code. It's potentially malicious. So what can it do with that, and why is that kind of bad? So JavaScript in the pack file isn't like JavaScript on a website. You don't have the full range of functions to put stuff on the screen and talk to the DOM and all that kind of stuff. These are all the functions. This is essentially the API that pack scripts have access to. And the 2 that really stand out to us is DNS resolve and is resolvable. So DNS resolve, as you might expect, takes a host name and returns an IP address, and is resolvable takes a host name and returns true or false. So these are interesting because they let the pack script talk to the outside world. So we have sensitive data going in, and we now have a way to communicate with the outside world. So putting it all together, here is our very simple malicious pack script. And what it does is it takes the URL, checks if it's HTTPS and therefore potentially sensitive. It then appends .leak onto the end. So in this case, .leak is a domain that's controlled by the attacker. And then it replaces all the special characters with this dot. For example, we have a sensitive URL there with a nice auth token in. And the script will convert it into this string and then do a DNS lookup. And the attacker receives this sensitive token back to their DNS server. So that's the attack. And of course, if it can't fit in a tweet, then it's not a real vulnerability, and it fits very nicely into a tweet there. So going back to the overall attack, the malicious gateway. So as we said before, malicious gateway can intercept any plain text HTTP traffic. Easy. But if we're talking HTTPS, then the attacker can't intercept HTTPS traffic. But if we now are leaking every single HTTPS URL, so the malicious gateway tells your laptop to use a malicious pack script, and now it's leaking all the HTTPS URLs, and then the HTTPS traffic is going to the server, so we can sniff HTTPS URLs and modify plain text HTTP traffic. So just to kind of sum this up in a nutshell, pack files allow attacker-controlled JavaScript to see every single HTTPS URL before it gets requested by the browser. The pack file can then leak that data to an attacker via DNS. So the whole point of HTTPS is to protect sensitive data on untrusted networks, but with WPAD and pack, an attacker essentially can do an end run around HTTPS. This is the second title we came up with. This is my favorite one, Apocalypse Now. I'm quite pleased with that one. Okay, so demo time.
Right. You might have to bear with us on this. We didn't realise we wouldn't have an Ethernet connection up here, so we're actually trying to do these demos live through the Wi-Fi on my phone. We'll see if it works.
If it works, it'll be a miracle. Okay, so the setup we have is, on the right, we have a VM, which is the victim. And on the left, we have our attacker with a fancy control panel. So I'm going to open up Chrome. So at this point, the malicious gateway has already sent the malicious pack file. And you can see at the bottom here, we've got already getting tons of URLs being leaked by Chrome. So I'm now going to search for something. So everything you do on Google, it goes over HTTPS. And as you can see, as I was searching, literally as I was typing, it's being leaked to the attacker, and it's appearing on their side. And now I can browse to Wikipedia, which is HTTPS. I can just, browse around Wikipedia, and you get so much traffic here at the bottom, all the URLs being leaked, and at the top is just pulling out the kind of interesting stuff, the actual pages that you're visiting. So that's that, and we can search for something else. So again, DEF CON sites is HTTPS. Yeah, so there we go. So that's what we can just do literally just by leaking everything. And thank you. So yeah, most websites these days are HTTPS, and we can see that stuff now with this attack, which is quite nice. Right, I'm now going to hand over to no, not yet.
You could go.
Okay, so passively seeing this data as the user browses is quite nice, but we're impatient. As an attacker, they may be connected to our malicious hotspot only for a short amount of time. So the challenge we set ourselves was to actively steal as much data as possible using only URLs. Now remember, this attack doesn't let us completely break HTTPS. We can't see everything. We can only see the URLs, including the path and the query string. We don't get any post data. We don't get any cookies, any headers. We don't get the responses, the response bodies. So we have this kind of superpower, but it's a really limited superpower. But limitation is good, and it lets us be creative. And one of the key things is that because the web isn't 100% HTTPS yet, the malicious gateway can still inject stuff into the HTTP pages. So we can get the user to visit our malicious web page and then start messing with their browser. For example, captive portal pages, which I'm sure everyone has encountered since they've been in Vegas. Okay, so we came up with a few basic techniques that let us do pretty much everything that you've seen in the demos so far, and then the demos we're going to show you. So one of the simplest ones, which works really, really well, is taking advantage of 302 redirects. So the idea is that we make the user's browser visit a known URL that's not sensitive, and then that URL redirects to a sensitive URL with sensitive information in, we can then steal. So for example, if you're logged into Google and you go to this URL, so plus.google.com/me/posts, if you're logged in, it will redirect to a URL with your user ID in it. So now we know who you are on Google. The same goes for Reddit. We can get your Reddit username if you're logged in there. And the very simple way to do this is literally just to put, say, an image tag on a page. It won't be visible, and it's not even an image, but the browser doesn't care. It will go and request that URL, and then we can leak that via DNS. So, for example, that would be sent to the attacker, and we'd get the username for Facebook. So that's the first technique. The second technique we're going to use, which you'll see in the demos soon, is for dealing with kind of one-time auth tokens. So perhaps we do this redirect. So the user's browser redirects to a URL. We can leak the token. But the problem is that the attacker wants to use that token. And if the user's browser gets there first, then that token's no good to us anymore if it's a one-time token. So the attacker wants to use it, but we want to stop the victim browser from requesting it. So the pack script, as well as just leaking the data, we can say, actually, if the URL matches this exact pattern, then return a proxy that doesn't exist. The user's browser won't be able to resolve the proxy. That URL won't get fetched, but we can still leak it to the attacker to use that data. Now, the third trick we came up with, which was quite fun, is essentially what we want to do is load a page that the user is logged into, and that page will have loads of stuff on it we want to get, and it will be loading lots of URLs that we want to leak. But we don't want the user to know that this is happening. In the past, things like iframes would be really good for this. We could create a tiny invisible iframe, load a URL in there, and we'd get all this stuff loaded. But iframes tend not to work these days because most sites use X-frame options, which says don't allow this site to be framed. So we came across something called pre-render. So pre-render is something that Chrome invented first, and it's now in Edge as well. And essentially what it does is this HTML tag here, and what it says is completely load this page in a kind of hidden window off screen. Load it so it's ready, so when the user actually clicks that link, it'll all be pre-rendered and ready to go, and it'll appear really quickly. So like Google uses this, so often the first hits on a Google search result will be pre-rendered, so when you click it, it looks like it just magically appears really quickly. So what this lets us do is load a known URL that fetches other sensitive stuff. So for example, if I load your Facebook photo album or your Google Photos page, it will go and request all the thumbnails of all your photos. Now these URLs are always on kind of CDNs, so they're over HTTPS, but they're not authenticated at all. So they have these long, random-looking URLs which are impossible to guess. But if we take that URL and load it in another browser, you don't need any cookies, you don't need to be logged in, you can get that data. So pre-render is good for that, and you'll see some demos of that in a sec. Right, over to you.
Let's see if we can see this in practice. So find our VM again. So in this case, we have the same as before, the user's there, but we've managed to force them to a web page we control and are able to inject content to. So we've chosen a particularly complicated, secure captive portal, so they'll be on there for a little while. On the attacker side, we can start the attack. So hopefully, if I click this button here, we'll start to see information coming back from that user's browser session. So we've already been able to grab their Google ID, Facebook ID, and name from Google. This is where we cross our fingers and hope the next bit works.
Oh, yeah. Come on. You do it.
Fine. So it looks like pulling the Google Images hasn't worked this time.
Show the video.
I might rerun it, see if we do it. But we can also, so you can also see we can also get their Twitter ID, LinkedIn ID, and their employment from LinkedIn, GitHub ID. This is just a really small subset of services that we were querying here, but there's a lot more we could do with that. I'll try just rerunning it, see if we get anything else or not. But essentially, that allows any captive portal to completely de-anonymize the user. Here we go, the images as well. De-anonymize the user that's connected to their gateway and get all sorts of what we would call, I guess, public but sensitive information about that user. And you can see we can also go into these images. Oops. We can actually get the full-size image just because it's served from a CDN. They're all there, and we just grab those files and kind of get all that offline data from them. So, demo number 2. We're doing well so far. So, to summarize that, if we force the user to request a web page or URL, we can get identifying information from it. We can then use those IDs and usernames to kind of get further information, so further public information, but information that we wouldn't otherwise have. So in order to do this, we need to create a bit of a C2 infrastructure between the user's browser, the pack JavaScript that's running on their system, the DNS server we're using for leaking information, and the malicious and the web server that we're using to kind of control all of this. So the first thing we have to consider is DNS. So leaking data over DNS. DNS actually has a kind of limited character set, so we can't just throw in any data we want. It's got to be within the kind of AZ0-9 underscore and hyphen range, I believe, and obviously periods. You can have a maximum of 63 characters per subdomain on a DNS lookup, and a total maximum of 253 characters. And that's just to do with the way that DNS has been set up. So what we ended up doing was base 36 encoding all of the data, not the most efficient, but very easy to do. Splitting long data into multiple host names, so multiple subdomains and host names, and then performing those lookups or more than one lookup for each leaked URL if the resulting DNS query was more than 253 characters. And then this is decoded and reassembled on the attacker's DNS server. So that's how we get the information out. We implemented an API interface between the victim's web browser and the PAC script running on their system. So the PAC script decodes and JavaScript evals any domains that end in the .etld. It'll encode the eval results of .rtld host names and send that back to the server, and it will leak all URLs by default. We added a small number of functions just to help out what we're doing here. So add block URL, so tell the PAC script to block all requests to a specific regex URL. Add a leak URL, so if the URL matches the regex there, it'll leak it to our server, and then clear everything just in case we need to clear everything down and return the PAC to a known good state. And this is kind of how all of that looks. So the top two portions are on the user system. So the injected JavaScript running in their browser is communicating to the PAC script running on their system via DNS lookups. The PAC file leaks encoded data to our DNS server. The DNS server passes that data back to our control web server, and we can serve commands to the browser from our control web server. So it's a bit of a cycle going on there, but that's kind of the overview of how what we're doing works. So, kind of getting information about who somebody is was good. And we were chuffed with that. We thought, right, we're really on something. But we can do better. And so we're kind of doing this research over a period of months, and kind of just these things, ideas are coming up to us as we're going through. And one of the things we were quite interested to look at is OAuth. So OAuth, for those who don't know, is a way of allowing a third party to authenticate users to your website. So there's some really big OAuth providers. So Facebook seems to be one of the biggest, Twitter, LinkedIn, Google, Yahoo, and Microsoft. And these services allow websites to hand off the authentication to these central authorities. So you would have all seen it, sign into this site, sign in with Facebook, sign in with Google. You just click those buttons. If you're logged into Facebook or Google, automatically you're logged into that site without having to type in your username and password. This is great from a usability perspective. You don't need to remember another set of credentials. It just all works, theoretically anyway. OAuth has a number of ways of passing tickets and tokens between the client application and the central OAuth server. But one of the more common implementations is using URL parameters via 302 redirects over HTTPS. So we thought, can we force this user to attempt to OAuth authenticate to a large range of services, intercept the final authentication token, and replay that ourselves? And that's going to be something that I'm also going to attempt to demonstrate. So again, user's still here, trying to fill out their form, password. Okay, they're going to be there a while. So we kick off the next attack. And you can see this one's particularly quick because we're only using 302 redirects. We're not trying to do the pre-render pages, which we have to do in serial, so only one at a time. This is going quick, lightning fast. From the attacker's console, we've now got all of these potential OAuth sessions. So if I, for example, open CodePen in a new incognito window, theoretically, good, that bit works. Yep, brilliant. I'm now logged into CodePen as that user with that being their icon there. Keep going, we've got loads of other services. So, for example, developer.mozilla, got that account. Someone's of interest, so I don't know if anyone's used ForShared before, but it's a cloud storage platform, so we can grab that and then start grabbing their files from that platform. And we've got full control of these accounts at this point. So we're just logged in as if we were those users. Demo's going well now. Yeah. Right. Back to the the slides. So this could be done passively. We could wait for a user to log in, but as Paul mentioned, we're kind of impatient, so we can force this. And if you're only using the 302 lookups, you can actually force a large number of authentication attempts against a large number of services very, very quickly. The user won't see anything necessarily when they go to log back into that service. In our experience, they won't see failed login attempt to this or anything else. So it's pretty blind from the user side of things. And it does allow attackers to gain full control over the victim account.
Okay, so we've shown you a few demos, which we're quite pleased with, but we want to go even further. So we've stolen some of the kind of accounts that most people don't care about. I mean, you tend to use OAuth for things that you can't be bothered to create an account. But we want to go after the good stuff. So we're going to attempt to get into your Google account now. So the way that Google works is quite interesting. They have lots of different domains, and you can't share cookies between top-level domains. So what happens is that when you log into Google, most of your cookies go onto the main google.com domain. And when you go to another website like YouTube or Blogger or one of the regional Google search sites, then there will be a kind of first-party SSO. So that will use say google.co.uk will ask the main site for an auth token, and it will use a 302 redirect. So we can steal that. So like this. So it will go accounts.google.com, please log me into google.co.uk, and it will say, OK, you're logged in, that's fine. Here's a redirect, here's an auth token, and then it will go and set the cookies on the local site. So, and then you're logged into google.co.uk. OK, and actually, do this together. The second demo we're going to see is stealing stuff from Google Drive. So again, when you download stuff from Google Drive, there's a few different ways it works depending on how you got the file. So we're looking, in this case, at files which have been emailed to you and that you saved to your Google Drive. What happens when you click to download a document is you start off on drive.google.com, and then it will do a redirect to googleusercontent.com, which is kind of unauthenticated, but it uses an auth token. And it kind of does this couple of redirects back and forth between the two different sites. But eventually, we can get the auth token, essentially, and download the documents. So I'm going to show you that demo. I should point out that none of these are vulnerabilities in like Google or any of those OAuth sites. This is just because we can steal the HTTPS URLs. OK, so I'm going to click this button, and we'll see. There we go. So we can see the URL here. It's got the auth token in it. And all I'm going to do is literally just open that URL in a private browsing window. So there we go. I'm now logged in to google.co.uk. So like I said, this isn't your main Google account. So we haven't got like the crown jewels, but we can still do quite a lot of stuff. So if I search for like my email, I can't type. So we get a summary of what's in your Gmail inbox. I can't click on those, but I can still see a summary. I can do my photos. I can do my home address. There we go. I can do my location. My location isn't working. OK, but another thing we can do is if you happen to have location history turned on your phone, then Google is basically tracking it everywhere you go. And because Google Maps is kind of, again, regional, it's not the main google.com site, you can go to your timeline. Come on. Does it stop working? Oh, no, it's getting there. It's just taking a while. So there we go. You can see everywhere we've been in Vegas, all the various places we've been. Where did we go today? It's being a bit slow. But anyway, we thought that was quite nice. Thank you. Yeah, okay. Right, we've got to get on. Okay, so I'll hand it back to...
Do you want to do the Google Drive demo quickly?
Oh, Google Drive, yes. Thank you. Right. Okay, get rid of that. So Google Drive, click the last button. And hopefully we'll see some stuff pop up. There we go, so you can see all the URLs going through at the bottom. And now the attacker server is going to download those to the server. And then we can load some of these things. How do you middle click? Open it. Fine. Right. So if you save some passwords to your account, that's a PDF, that's someone else, and that's some passwords there. Right.
Great. So that last demo that was all Paul's work. He spent ages doing that, and I thought, well, I can't let him have the best demo of this talk. So I spent a little while looking around, thought I'd target Facebook. I was like, right, there's got to be a way of getting somebody's Facebook account, right? And there was. And up until about 3 days ago, this worked. It was only when I went to record a video of showing stealing somebody's Facebook account using OAuth that it all stopped working and Facebook broke it. So I don't have a demo of that, I'm afraid. Facebook didn't break it in the sense that they fixed it, they just broke it. So the attack was through the forgotten password functionality. There's an implicit authorization between Facebook and Microsoft's OAuth. So if you've signed up to Facebook with a Microsoft account, you can hit forgot my password, type in your email address, and there's an option to just reset it via the OAuth authentication to Microsoft. But that now asks you to log back into your Facebook account. So to reset your password, you have to log into your Facebook account. Anyway, so I'll move on from that. So one of the kind of key points we thought we were going to get from this was people turning around and saying, so what, I use a VPN. VPNs allow us to kind of travel safely over hostile networks and kind of should protect us in this area. Right? So just to go back to our previous examples, so a malicious gateway with users connecting over a VPN, user tunnels through to their VPN server, and then all traffic goes out to the internet from that VPN server. So the attacker can't sniff HTTPS URLs, or they can't intercept traffic. Using the pack leak, similar sort of thing, we tell them where the pack file is, they've got their secure tunnel set up, but the pack file is situated on the local network. There's no route from the VPN server to where we're hosting the pack file. And then the user, so because the browser can't find the pack file, it'll just ignore it and just connect directly out to the internet. So what if we move the web server hosting the pack file to the internet? So we tell the client that the pack file's on an internet-accessible server. They connect to their VPN server. They can now access that pack file and connect to the internet. So at this point, we are sniffing the URLs as we were before. But we can go one better than this. What are pack files supposed to do? They're supposed to specify a proxy. So if we stick our proxy server on the internet as well, we've now got the users' traffic coming out of their VPN endpoint, leaking the HTTPS URLs to our DNS server, proxying all of their HTTP traffic before it's even hitting the intended target. And this kind of blew our minds. This is really quite cool. Yeah, it shouldn't work like that, should it? So many VPN clients do not actually clear the proxy settings obtained via WPAD. We tried a few, and I'll run through those shortly. The traffic's tunneled all the way from the VPN endpoint through our proxy on the internet before it hits the intended destination. So the affected software on this, OpenVPN, is affected. They are working on a fix, but to this point, it has not been released. So there's no way of mitigating this through an OpenVPN server configuration. Private internet access. I don't know who uses private internet access in this room for VPN configuration. We reported this issue to them as well as OpenVPN. They have fixed it, so they are their client's based on OpenVPN, but they've implemented a client-side fix to disable WPAD to kind of fix this. And kind of more corporate VPN solutions, for example, Cisco AnyConnect, actually have an option to say, push your own proxy or kind of completely wipe all proxy settings before coming this way. The Windows built-in VPN clients aren't vulnerable to this. They actually, looks like they've thought about this issue and have disabled WPAD by default on these LTTP and PPTP connections. Yeah, it speaks for itself. So Paul's third work of art there, the rejected vulnerability title for this issue. So the next response, so what? I don't use Windows. Yeah, actually other operating systems do use WPAD and PAC. So OS X does, iOS does, Android does. Okay, not by default. So it's not quite as bad as on Windows, but you do need to be aware of it. I think that's pretty much everything I covered.
4 minutes left.
Yeah, fine. So to mitigate this, first thing you do on a Windows system is turn off WPAD. Seriously, turn off WPAD. There's no good reason to have it on. So if you still need to use PAC, which a lot of organizations will need to do, turn off WPAD and configure an explicit URL for your PAC script. So you can do this securely over HTTPS to an internal server, or you can actually serve it from a local file on Windows if you specify another registry key, so we'll just pull it from the disk. And those are really the only two secure ways of doing or distributing PAC files. To mitigate VPN, turn off WPAD. Only so many times I can say that. VPN is safe if WPAD is enabled. If the VPN environment requires a proxy server to get out to the internet, then it effectively mitigates this issue. We can't chain proxies using PAC as far as we're aware. Or if the VPN server pushes an explicit proxy configuration, then this won't be an issue, as I say, and that's certainly an option on a lot of the enterprise-level VPN solutions. So the good news, we reported this issue to vendors back in March, and a lot of them have fixed it. So Apple came out pretty quick, releasing fixes for OS X and iOS, and Apple TV. Didn't know they still did that, but Google Chrome patched just a few weeks ago. In fact, I was setting up these demos and I couldn't work out why they weren't working the other day. It's because my Chrome had automatically updated and I just had to kind of downgrade it again. Android patched in July. Firefox, waiting on a patch for this issue, but it's also not the default configuration in Firefox, so it has to be explicitly enabled. And Microsoft have a patch pending. Again, it's slightly different on Microsoft, certainly on Edge and Windows 10. It does some really funky caching stuff, so it's really not quite as big as a deal with that. How long have we got? Running through 2 minutes. So we're actually not the first people to spot this issue, but we were the first to report it. So there was a talk at Black Hat this year, literally last week, on this exact same issue. The guys didn't report it to any vendors for some reason. Ben Venice, I hope I'm pronouncing that right, Bas Venice, sorry, reported this issue to Google and Firefox literally 2 weeks after we did. So plenty of people looking in the same place. There was a master's thesis from May this year which outlined this issue. There was a Russian blog post from June last year outlining this issue. And there was a Stack Overflow question from May last year outlining this issue. Lots of people have found this. Nobody reported it to the vendors. Interesting. Not sure if we've got time for that slide. So, to summarize, network-based attackers can inject PAC scripts into browsers. PAC scripts can leak all HTTPS URLs via DNS to an attacker, at least on unpatched systems. We showed how to de-anonymize users, steal OAuth tokens, access photos, location data, and documents. A VPN won't necessarily protect you against a malicious proxy. Now go turn off WPAD.
Very quickly, I'll just say we're going to be releasing all the code for all the demos, like as soon as we get back home and have had some sleep. So it will be on GitHub. Just watch our Twitter feeds, and we'll let you know when we've released it, if you're interested.